6.13.3 Work in polytropic processes. Work for a steady device with one inlet and one exit can be written as this. So now we are going to express the work for a steady device undergoing a polytropic process without irreversibilities. So polytropic process can be expressed as pressure times specific volume to the nth power is some constant. So we can write V equals some constant divided by pressure raised to the power of 1 divided by n. So plug V into the equations. So the work during the polytropic process can be expressed as this. And this is when n is not equal to 1. And if n is equal to 1, the work expression can be expressed as this. So note that this is the work expression for a steady device undergoing a polytropic process without irreversibilities with a single inlet and single exit. Additionally, if it is considered as an ideal gas, we use the ideal gas law, PV equals RT. The work expression can be expressed as follows. When n is not 1, the work expression is expressed here. When n is equal to 1, the work expression is expressed here. So this expression is for ideal gas. Steady flow device. Undergoing polytropic process. No irreversibilities. One inlet and one exit. Let's see an example. An air compressor operates at steady state with air entering at 1 bar, 20 degrees Celsius, and exiting at 5 bar. Determine the work and heat transfer per unit mass passing through the device in kilojoule per kilogram. If the air undergoes a polytropic process with N equals 1.3, neglect changes in kinetic and potential energy between the inlet and the exit. Use the ideal gas model for air. In this problem, air is considered as an ideal gas and it undergoes a polytropic process. No irreversibilities is associated with the process and it operates at steady state. The pressure at the inlet and the exits are given. So using the pressure ratio, we can determine the temperature at the exit. P1 over P2 equals T2 over T1. And this is for polytropic process of an ideal gas. So we can solve it for T2. N is 1.3. So T2 is 425 Kelvin. And let's first determine the work associated with the process. N is not equal to 1. So we use this is R for air. And the negative value indicates the work is done on the system. Now we are going to evaluate the heat transfer during the process using the energy rate balance. For ideal gases, the enthalpy is a function of temperature only. So temperature at the inlet, 20 degrees Celsius or 293 Kelvin, which fall between these two numbers, we can determine enthalpy by interpolation. So H1 can be determined 293.17 kilojoule per kilogram. At the exit, temperature T2 is 425 Kelvin. 425 Kelvin, between these two numbers, the enthalpy is between these two numbers. So H2 can be also calculated by interpolation. 426.35 kilojoule per kilogram. So this is the heat transfer rate per unit mass flow rate during the process. The negative sign indicates heat is rejected to the surrounding.